The number of people are starting to slow down coming into the room, so I'm going to go ahead and get us rolling here. So welcome to the last CACR Speaker Series talk of the 2020-21 year. And it's my great pleasure today to introduce Gary McGraw as our speaker, who's going to be talking about security engineering and artificial intelligence. For those of you who maybe haven't kept up with Gary's latest activities, he is most recently the co-founder of the Berryville Institute of Machine Learning. And prior to that, he had a long, distinguished career as a globally recognized authority in software security, where he wrote 8 best-selling books, 100 or more peer-reviewed papers, and most lamented by me, he spent 13 years doing the Silver Bullet podcast for IEEE Security and Privacy, which came to an end about a year or two ago, and I deeply missed that. He also serves on the Dean's Advisory Council here at Luddy and is an IU alumni with dual degrees in cognitive science and computer science. And as we were talking about beforehand, got a career award from Luddy, which I think was premature back in 2013, as he's obviously still alive and careering.
So I guess I was declared dead.
So with that, I welcome the alive and kicking and still careering Gary McGraw.
Thanks, Vaughn. Really appreciate it. Let me share my screen here. Hopefully I picked the right thing. So I'm going to talk about machine learning stuff today, and security in particular. What I'm not going to talk about, though, is using machine learning for security. Instead, I'm going to talk about the security of machine learning itself. My view is, if you're going to do machine learning for security, you better secure the machine learning stuff first. Otherwise, what's the point? And so I'll tell you a little story about what we've been working on over the last couple of years at BIML, and what BIML's doing, and then I'll tell you about some architectural risks that are built right into machine learning. Let me go over here. So Vaughn gave me an introduction. This is kind of the 3 things that I do: playing music and wielding lightsabers and burning big giant bonfires. I really am sad that I'm not in Bloomington giving this talk today. I've given some talks for CACR before in the big law room, and I really love interacting with people in person. I'd much rather do that than try to give yet another Zoom talk. But we do what we can do in the pandemic. I'm happy to say that I have gotten both of my vaccine shots, and next week I will be cleared and ready for getting back out into the world. Everybody get vaccinated. My number 1 message today is get vaccinated, period. So let me tell you about BIML. I retired from Cigital, which was a company that had about 500 people doing software security in 2019. And when I retired, I was thinking, you know, we've been hearing a lot about artificial intelligence and machine learning and all the progress that's been made. I wonder how much of that is real. And the reason I wondered that is because back in Indiana, when I was working on my dual PhD, my colleagues and I worked a lot directly in connectionism. I was working with a guy named Doug Blank, who got his PhD and is still doing connectionist work at some startups in San Francisco, and Lisa Meaden, who became pretty famous for her connectionist work in robotics, and Jim Marshall, who's a professor in New York City. And all of us, when we learned to do stuff, like when we were learning about machine learning, we built things, and then we tried to publish that work. So we knew a lot about machine learning from a very hands-on perspective. And I wondered if we really had made all that progress, because the kind of claims that you read about in the press are just absolutely astounding. And so we decided we would form a research group and just do some reading of the literature, read some papers, see what's actually going on out there in the world. And through that activity, it became really clear pretty quickly that the biggest progress that had been made in machine learning is computers were way faster than ever before. There were just huge amounts of cycles available to do computation, and data sets were likewise really huge and highly available. So big giant piles of data and big amounts of cycles together made the old algorithms work better than they worked back in 1989, say 1995. And so much of the progress in the field is not coming because of gigantic changes in architecture or different learning algorithms, but rather because our computers are way better. That was kind of surprising. Now, there are some progress things that we've made, like convolutional neural networks and the idea of running a thing against itself, like the AlphaGo stuff. But by and large, machine learning is pretty much the same. And back in those days, we had some issues in machine learning that could lead to risk, like, say, overfitting. And so when I started digging into this stuff, I thought, gosh, I can't ignore the fact that I'm well known as a security guy. So what about security? So we immediately started thinking about ways these systems could be attacked and put at risk. We started reading the papers about that stuff. There's a lot of academic work in that area called mostly adversarial machine learning. And we eventually published our work under the BIML rubric. BIML stands for Berryville Institute of Machine Learning, under the Creative Commons. And you can get that work that I'm going to talk about today, where we identify 78 security risks that are directly associated with machine learning systems. This work is meant to inform people who are either designing new machine learning systems or, more importantly, applying existing machine learning systems. So we've been talking with Google and Microsoft and Amazon and OpenAI and Facebook about their use of machine learning and how our work impacts the kind of risks that they think about when they're adopting that stuff. We are not going to stop the world from adopting machine learning technology. That'd be like trying to stop a flood with your hand. But we are going to do what we can to make sure that we have intelligent, rational conversation about the risks that are associated with this technology, including bias risk and all sorts of other things. So this is a little cow. One thing you should know about BIML is Berryville is a tiny little speck of a town in a tiny little speck of a county at the very tippy top of Virginia, where things go like that. And in fact, the center of the cow there is the shape of Clark County itself, which may have more cows than people if you count them all up. So it's kind of fun to be doing this cutting edge machine learning work in the middle of nowhere in Virginia, but that's the way the internet is these days. That's pretty cool. So I want to bring everybody onto the same page with regards to what we're talking about when we say machine learning and when we say artificial intelligence, using some slides that I stole with permission from Melanie Mitchell, who was also a student at Doug Hofstadter's at Indiana and at Michigan, and who recently wrote a book called Artificial Intelligence, a Guide for Thinking Humans, which I highly recommend. Artificial intelligence in the 50s was supposed to be solved in a week, according to the McCarthy meeting that happened in, I guess it was 1956 or maybe it was 1959. And it was going to be really easy. And wow, computers were going to do this amazing. There were going to be artificial intelligent things in the 50s that would only take a week, really. So that turned out to be wrong. But we made a lot of progress between the 50s and the 80s on AI. A lot of it was around things that we take for granted today, like how to best do search, indexing, some language processing stuff. And AI was a pretty big field. You can see that blue box. Machine learning was a little subsection of that. It was mostly Bayesian learning in the day. And then deep learning or neural network stuff was a tiny little bit of that. You might be familiar with the book that Minsky and Papert wrote called Perceptrons, which kind of killed the field for about 30 years until McClellan and Rumelhart came along and kind of resuscitated deep learning in the very late 80s. So in the very late 80s, it started looking like this. Machine learning got bigger. There was more connectionist stuff going on, but deep learning itself, convolutional neural networks and very big, deep networks with lots of layers was still a small part. And then this happened around 2010. Deep learning just took over everything. And so basically what's happening in the press is when you hear talk about artificial intelligence, is the press is really talking about deep learning. They're not talking about AI writ large, because there's a lot of other stuff going on in AI. And there's other stuff going on in machine learning than deep neural networks. But all of the results that we're reading about are really about these deep learning systems, and that's what I'm going to mostly be focusing on today. So zooming in, the notion that is driving the idea of machine learning is you want to build an auto-associative map between input and the output that you want. So you put some input into a system, you get some output, you might not be happy with it, you make the output, you say, well, this is what we wanted, this is what we got, here's some deltas, and then you swoosh all that back through the network using an algorithm like backpropagation to change weights and thresholds in artificial neurons that are set up in layers. Now, the reason artificial neurons are set up like that is because they're inspired by neurophysiology. And so if you think about the visual system in the brain, you can see a picture here where, a picture of a dog comes into your eyeball and your retina does edge detection, simple shape detection starts happening. Then it feeds into the visual cortex, and you've got 4 layers of visual cortex. So V1 through V4, and that's where simple shapes get put together into complex shapes, and then faces and objects get recognized, and you can say, oh, that's a dog. And that is a very quick overview of how your perceptual system for vision works. You can think of it as feeding forward through this network of neurons into your brain, which is made up of neurons. And so if you take a convolutional network, you want to sort of do the same thing. So we have some input that's a picture of a dog, and we've got some layers, and the layers do various different levels of abstraction. And at the very end, we have a classification module that takes the activation out of layer 4 and decides what that picture is. And it says, oh, in this case, it's 85% dog and 15% cat. Now that should clue you up that something is going a little bit strangely here, because I don't know about you, but I don't think, oh, that's 85% dog when I see a dog. But that's the way these neural networks work. And it's very important to understand that though this is inspired by things like the visual system in the brain, it is not the same as the visual system in the brain. And we have a long way to go to really get to understanding. So machine learning is doing some astounding things using auto-associative predictive generative networks like GPT-3, but they're not doing things the same way that people do them. And that's an important thing to keep in mind, especially when you read all of the highfalutin press out there, even in publications like the New York Times. So what we decided to do in our work when we were reading this stuff was to build a generic machine learning model and identify some components in that model that we could then use to think about security risks. We wanted to consider each of the components individually and try to tie particular security risks to those components, and then put them all together and talk about them as a collective, and also do some system-wide risks. So that was basically our approach. It took us about a year to do this work. We published this last January, not January 2021, but January 2020, right before the world turned off for COVID. And so we're looking forward to getting out and talking more about this out in the world. But in the meantime, we've been interacting with people on the net, just like everybody has. So we identified 9 basic components. In our picture here, you can see those 9 components. And in this case, processes are ovals, like data set assembly is a process where you take raw data and you assemble it into the data sets that you're going to use for training and validation and testing. And collections of stuff are rectangles. And so in this diagram, arrows kind of represent information flow. So we get raw data in the world, it gets assembled, we train up a network, we do some evaluation, we end up with a model, then we have an inference algorithm, and we have raw data that feeds into inputs, and we can use the inference algorithm to get the outputs that we desire out there operationally in the world. And we used this model to think about risks in each component, just basically using our experience as security experts to approach each of these components in turn. So without further ado, let's dive into these. Instead of covering all 78 risks, what I'm going to do is tell you about 18 plus 2, so really 20 risks out of the 78 that we identified, to give you some flavor for the nature of these security risks and what we mean when we say risk. And then at the end, I'll cycle back and give you our view of the 5 most important risks in machine learning. So I'm not going to give it away when we come to those, but I'll, in the end, we'll give you the top 5 so you can think about those as a takeaway message. So data really play a super central role in machine learning systems. In fact, they're really the most important aspect of machine learning and also the most important aspect of machine learning security. My estimate is that about 60% of the security risks that you can find in a typical ML system are directly related to the data that the system was trained and operated on. So there's lots of raw data out there, and we're using that lots of data to do things like train up GPT-3 on the web crawl, which is literally hundreds of millions of data points. And those raw data, you need to realize, can be manipulated by attackers, because if we're just going out and grabbing raw data out of the world, then what happens if we grab the wrong data that some attacker has already attacked? So let's think about 2 examples of risks that we identified out of 13. The first is data confidentiality. Now, we all know in security that we sometimes have data that are private or confidential, and we don't want those data to be exposed to the system outside of the system. And in this case, a machine learning system that's trained up on confidential or sensitive data, say medical data, will have some aspects of those data built right into it through training. And so if you have attacks that kind of extract that sensitive confidential information from a machine learning system indirectly through known use, you can have a really serious problem, and through normal use. And that is a very, very standard issue thing to do. It's pretty easy to pull some of the output that you use to train a model back out later. That means you need to be careful about the confidential data that you cram into a machine learning system, because it's in there. And so the question is, well, what about things like GDPR? And we're not really sure what the answer to that is. You know, if you have sensitive data that are protected by what do you call it, regulation, and then you train up a machine learning on that system on that, should the machine learning system be regulated too? Nobody's really sure. So that's an interesting point, and that's risk number 1. Another example is trustworthiness. Data sources are not always trustworthy or suitable or reliable. And so one of the things you have to think about when you train up one of these systems is, how might an attacker tamper with or otherwise poison raw input data? What happens if those input drift over time or change or disappear? And so that's 2 examples of risks associated with raw data, which then directly impact machine learning systems out of 13. So there are 11 more risks like that in the paper and for that component. Let's move on to component 2. One of the things about machine learning is that the raw data have got to be transformed into machine learning format that, you know, a machine learning system can use. Often the data are in a format that's not appropriate for that. And so pre-processing is really critical, and it's also important for security. We also have a kind of important distinction that I want to mention for the first time here in online versus offline models. In machine learning, while you're training the system up, it's online. And if you have a system that's operating and still being trained while it's operating, that's called an online system. Most of the time, in many uses of ML, you train up the model and you sort of freeze the model, and it doesn't keep learning when you have it out there operationally in the world. Of course, securing something that's offline is way easier than securing something that's online. And so that's a thing to understand here. So let me give you two examples of data set assembly risks. The first one is about encoding integrity. And integrity can be both introduced in a good way and also integrity issues exacerbated during pre-processing. So, if you pre-process the raw data, does that introduce security problems itself? Like, are you throwing away data that are really important, or are you downplaying features that are really critical that you didn't know about? One thing to understand is that bias in raw data processing can impact all sorts of things in the machine learning system itself, because data bias is a really critically important thing to think about in machine learning systems. And sometimes that leads to moral and ethical implications, which I'm going to talk about more later. But the way of encoding these things into sort of an input vector really makes a big difference. And what representational power you bring to bear has a huge impact on the behavior of a machine learning system. Related to this is this notion of annotation. The way data are tagged and bagged, or like annotated into features, can be directly attacked, and that introduces attacker bias directly into a system another way. So an ML system trained up on examples that are way too specific will not be able to generalize very well. And much of the human engineering time that goes into machine learning is really spent in this kind of process that no one talks about: cleaning and deleting and aggregating and organizing and just all out manipulating the data so that it can be consumed by an ML algorithm. That's the kludgy heuristic part that everybody wants to pretend doesn't exist. But when you do that kind of pre-processing, you're introducing risk and bias directly into the system yourself before it's even really getting started. So those are two examples out of 8 risks associated with dataset assembly. What we want to build are training sets and validation sets and test sets, and data are grouped into these 3 sets. The partitioning itself is very tricky, and it deeply impacts the future of machine learning behavior, because you want to make sure that your training set is appropriate for your final machine learning operational system, and you want to make sure that your validation set validates the whole model and just not just parts of it. And so this notion of building a good validation set is very, very important. Some examples of risks associated with this component. The first is poisoning. Of the first 3 components in our generic model, that is raw data in the world and data set assembly and data sets themselves, they're all subject to poisoning attacks, whereby an attacker intentionally manipulates data in any or all of the first components, possibly in a coordinated fashion, to cause the machine learning system training to go awry. Let me give you an example. There was an online system that was a Twitter bot called Tay that Microsoft released, and it put it out on Twitter. Tay was supposed to interact with other Twitter users and learn to use Twitter and learn to have Twitter conversations as a chat bot. Well, you know what Tay learned? It learned to be a racist, xenophobic, misogynistic asshole. And it learned it very quickly by just watching how people were behaving on Twitter, and trolls were trolling it. And it very quickly learned to be a horrible citizen. And it was so embarrassing that Microsoft took it off the net almost immediately after it was introduced. And that shows you, if you feed a machine learning algorithm bad things, don't be surprised when bad things come out the other side. That sort of thing happens. So Tay is a perfect example of that. Another example of a data set risk is transfer risk. Many machine learning systems, because of economic reasons, are constructed by tuning an already trained base model so that its somewhat generic capabilities are fine-tuned with a round of sort of specialized training. You might think about if you have a machine learning system that does circle recognition, and then you want to like fine-tune it into oval recognition. That might be an example. And it's cheaper to start with an existing system that's already been trained up than to start all the way from scratch. Now, a transfer attack presents an important risk in this situation, because if you have a pre-trained model, the risks that are in that model get carried right over to the fine-tuned model. And so There are a number of cases in which Trojan functionality can be inserted. There's a whole literature. Unfortunately, the people in machine learning are calling this backdoors, but it's not really backdoors, it's just Trojan functionality. And you can insert that functionality during this transfer process. So those are 2 of 7 risks associated with data sets. Let's move on to component number 4. I mentioned online systems before, and I'm going to go into that now, but this kind of the learning algorithm is kind of the technical heart of machine learning, but there's less security risk here than the data bring to bear. That's the kind of interesting thing. There's not none here, but most of the security risk, the technical risk, is coming from the data itself. And then we have the online versus offline thing. Of course, offline is easier to secure, as I mentioned before. So let's give 2 examples of this. We'll start with online. An online learning system that continues to adjust its learning during operations might drift from its intended operational use. So you might be interacting with this machine learning model and moving it away from doing the right things. So clever attackers can nudge an online learning system in the wrong direction on purpose. There's a famous story that we're not sure is apocryphal or not. We tried to dig up actual evidence of this, and there's some kind of post-production tangential evidence, but nobody ever wrote this down. And that is that the Google translation algorithm got very confused and into a very bad feedback loop when it started reading its own translations and training on itself. And that was a system that was online, and so it was making these crazy mistakes, but then it thought the mistakes were examples, so it learned that they were good, and it got into this bad feedback loop. And to this day, you're not allowed to feed Google translations into Google Translations for obvious reasons, if it's an online system. And so that's an example of what happens when online systems go wrong with that feedback loop. Or if you imagine an attacker nudging things in the right direction. Number 2 example here is reproducibility. Now, if you've read a lot of machine learning system papers like we have out of the literature, both peer-reviewed and stuff on archive, you find out very quickly that machine learning work has a tendency to be very sloppily reported. And there are many systems where they say things like, oh, well, we empirically decided to set this particular parameter to 5. And you're like, what does that mean? Well, what that really means in English is, oh, well, we couldn't make it work, but we set it to 5, then it started working. So we're going to tell you that we set it to 5, but not really why. That's what empirically set to 5. So if you can't reproduce results, this may lead to some overconfidence in a particular kind of ML system to perform as desired. And this notion of reproducibility is a big notion. It's a big problem in computer science writ large. And the idea of open data and open code can help to address that problem. But it really is a problem in machine learning to this day. There are a lot of heuristics and kludges that people use to set parameters. It's not really clear exactly why you do things sometimes, and it's something important to think about. So that's 2 risks associated with the learning algorithm. There are 9 more risks like that in the paper for that component. So let's move on to evaluation. Evaluation is supposed to figure out when's training done. Like if I'm training a thing on input-output pairs for millions of cycles, how do I know when I'm finished? And then how good is the trained model? That's where this validation and test sets from the data set assembly stuff come in. And I'll give you 2 examples of risks at this stage. One is overfitting, and this is something that we've known about since the 80s. A sufficiently powerful machine is capable of learning its training data so well that it just essentially builds a lookup table. It memorizes its data. And the unfortunate side effect of like perfect learning like this is an inability to generalize outside of the training set, and that's called overfitting. And with these gigantic models that we're building today, the overfitting risk is a real thing that we have to worry about. So that's one risk. Another risk is bad evaluation data set. A bad evaluation data set that doesn't reflect the data that a machine learning system will actually see in production can mislead a researcher into thinking that everything is working just fine, even when it's not. So you got to make sure that your evaluation set covers the space very nicely. If it doesn't cover the space, then you're going to end up thinking your machine learning system is better than it is because the evaluation stage was not done right. Evaluation sets can also be too small or too similar to the training data to be useful. So you think you learned about the world, but you really just learned about your training set. And you know what? Machine learning systems have an incredible capacity to learn what you told them to learn, but not what you wanted them to learn. I'll give you an example. There's a famous ML system that was supposed to discriminate between wolves and dogs. And so there were a lot of pictures of wolves, a lot of pictures of dogs, and you put a picture of dog and it would say dog, you say good, and put a picture of wolf and say dog, you say bad, and change the weights, whatever. You do that millions of times. And eventually you end up with a classifier that's supposed to classify a picture of either being a picture of a wolf or a dog. Well, it turned out that the training set just so happened to have an issue, which was that every picture of a wolf had some snow in it. And so the machine learning algorithm immediately noticed whenever there's snow, it's a wolf. And it was perfect on its training data, perfect on its evaluation set, but it did some really screwy things when it was put into production, when there wasn't any snow, or when there was snow in a dog. So, what it learned was to be a snow detector and to solve the problem that way. And the researchers thought that it was solving a whole different problem. That is an example of bad evaluation and something that my dear colleague Doug Blank used to call the not a K problem. In, I think, 1988, Doug Blank tried to train up a neural network, a very simple one, to recognize English words. And it was supposed to just recognize 3-letter words like a consonant and a vowel and a consonant like cat. And Doug wanted the machine to tell him what constituted a word with a bag of 3 letters. And he trained it up, vowel, consonant, blah, 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 for a bunch of training sets. And it got pretty good at its training set, but it ended up being exactly right on everything in its training and evaluation set by coming up with the simple rule: an English word is something that's not a K followed by something that's not a K followed by something that's not a K, which matched all of the data perfectly, but was not what Doug was trying to get done. So I still call that the not a K problem, invented at Indiana University in 1988. So those are some examples of risks, 2 of the 7 risks in the evaluation component. Let's move on to number 6, where we're thinking about input risk. This is very similar to the data set assembly stuff and the raw data. You see the raw data in the world goes to data set assembly and data sets, and then it also goes down directly to inputs. So many of the things that we already talked about when it came to data set assembly, about tagging and bagging and all that stuff, are very similar here at this level. Let me give you 2 examples though. And number 1 is very important. You've probably heard this term, adversarial example. One of the most important categories of computer security risk, we all know, is malicious input. And the machine learning version of malicious input has come to be known as adversarial examples. I'll show you some real adversarial examples in just a few minutes when we get to the top 5, because adversarial examples turn out to be one of the top 5. And we hear about things like the famous ML system that the researchers at University of Michigan trained up to do stop sign recognition, and then you put some tape on the stop sign, and lo and behold, it thinks the stop sign is a speed limit 85 sign, which is not very much like a stop sign. And if you're a car, self-driving car, and you think a stop sign says speed limit 85, that's not good. So they used adversarial input to do that work. Got a lot of press for that. That's one example. And another example is controlling the input stream itself. So a trained ML system that takes as its input data from the outside might be purposefully manipulated by an attacker. Maybe the attacker will blind a sensor with a laser, or maybe an attacker will put some special sauce into the data set, so then they know a way to trigger the machine learning system later to do the wrong thing. Oh, that's not a tank, that's a cat. Everything is fine. So there are 3 more of the 5 input related risks in the paper, and I'll tell you more about adversarial examples here in a second. Let's move on to component 7. This is risks associated with the fielded model, similar to evaluation risks in many respects. Example number 1 is a machine learning system that gets reused intentionally in a transfer situation, but somebody decides to reuse a network for something that the person that built the network did not intend them to use that for. And you know, I can just give you a real world example. I know everyone on this call has probably used a shoe as a hammer before. Shoes are very bad hammers. We've all tried it once and we're like, dang it, I wish I had a hammer because this shoe doesn't work very well. And just the same way, if you use the wrong pre-trained network to do some fine tuning on, that's improper reuse. Happens all the time in software systems, and it happens in machine learning too. And then risk number 2, model transfer leads to the possibility that what's being used might be a Trojan version or otherwise damaged. And so, you know, maybe you use the attacker puts some Trojan functionality in there that they can tickle later. So those are 2 of 5 risks at the model level. Finally, we get to the inference algorithm itself. This is what we put out there in the world that does something like either prediction or categorization. And these are risks that are associated with the fielded model. This is where kind of output risks begin to arise. We already talked about online systems, so I'm not going to talk about that one again, but that's a perfect example here where you nudge the thing in different ways based on its output. Number 2 is this problem of inscrutability. In far too many cases, machine learning systems are fielded without any real understanding of how they work or why they do what they do. When you integrate an ML system that just works into a larger system that relies on the ML system to perform properly, this can be a real problem. And, you know, this notion of we're not sure how it does what it does, but it seems to do the right thing all the time, so we're just going to ship it, is a gigantic risk in ML. There's an entire subfield called explainable AI that's trying to understand how these systems do what they do, so that when they don't do what they're supposed to do, we can both notice it and not allow the thing to do something catastrophic, like, say, misdiagnose a medical condition. And so those are 2 of 5 risks of the inference level. And then we get to the last component, number 9, outputs. System outputs, often the whole point. So direct output attack is pretty obvious. The direct output thing is example number 1. An attacker tweaks the output stream directly. So this impacts the larger system where the ML system is subsystem is compromised. There are a whole bunch of ways to do this thing. It's more like regular computer security. It's an interposition attack, really. Probably the most common attack would be just to interpose between the model output and the subsystem and the rest of the bigger system. Inscrutability makes this really highly plausible, because if you don't know what the ML system was doing or why it did its output the way it did it, then if somebody changes the output, you might not even notice, because, well, who knows how that thing works? So you sort of take for granted that it's right. And you turn off your anomaly detection, your natural anomaly detection a little bit. So that's one example. Another is provenance. ML systems must be trustworthy in many cases to be put into use. And even a temporary or partial attack against output can cause trustworthiness to plummet, and then people will start distrusting the ML systems in general, and that technology will take a hit. So those are 2 examples of 7 risks at the output level. We also thought, we need to consider risks not only at the component level, but risks that are either between components or over components, among components, across components. And we identified 10 system-wide risks in our work. I'll give you examples of 2 of them. The first is very important. black box discrimination. So you've probably heard that in some cases, machine learning systems can be biased. In some cases, the bias is racial bias or sex bias or you know, xenophobic bias. And these cases are very much real, and they lead to problems like not giving people loans or saying that somebody is more likely to commit a crime when you let them out of prison than somebody else just because of the color of their skin. And so black box discrimination, bias that's built into these systems because of the data sets they were trained on, is really important. Many data-related component risks lead to bias in the behavior of the ML system itself. And so ML systems that work on personal data or feed high impact decision processes like credit scoring or employment or medical diagnosis decisions pose a great deal of risk. When biases are aligned with gender or race or age, operating the system might result in discrimination with respect to one of those protected classes, and that can be a really serious liability problem. This is a real thing. There's a very nice PBS special that came out in April called Coded Bias. Anybody who's interested in this kind of bias behavior in ML systems, I would encourage you to watch the Coded Bias PBS special. It's pretty easy to find on the net. I will tell you this, this is a very controversial issue, even in machine learning in the field itself. Tim McGraw got fired from Google for bringing up some of these issues in a paper. And, you know, there's a big controversy over whether it was the paper or bias or, you know, how do we do social justice work in the machine learning field? And I tell you, even in our group of 4 researchers at BIML, when we read the paper that got Timrit fired, we were like, well, we had our own internal argument over whether that, you know, how that could have shaken out. And so these are very tricky issues. Even if you're cognizant of them, there's no easy solution. We really have to be aware that that's a problem. Number 2 is overconfidence. When an ML system with a particular error behavior is integrated into a larger system and its output is treated as high confidence data all the time, even if it has, you know, error behavior that we know about, users of the system may become overconfident in the operation of the system for its intended purpose and think that it's always right. In some cases, it's not right. So developing overconfidence in ML is made way easier by the fact that nobody really knows how they work. So when it starts doing weird things, you just go, well, it must be right. It's usually right. And then you end up in big trouble because you have overconfidence in a system that's not doing what you really want it to do. So those are 2 examples of 10 system-wide risks that we identified. So what I've given you is 20 particular risk examples out of the 78 that we identified in our work. And I would encourage you all to read that paper. It's easy to find if you go to berryvilleiml.com. That's our website. Under results, there's a thing called the architectural risk analysis, and that's where our paper is published under the Creative Commons. You can use it, cite it, borrow it, steal it. It's important that we talk about these risks. What I thought I would stop with and kind of cover last in this talk is the top 5 machine learning risks. So we've talked about 20, and there are different levels, but what I want to do now is just sort of rank them and give you a feel for what we feel at BIML is the most important risks in machine learning. The first one is probably the most commonly discussed attack. That's adversarial examples. I already gave you the stop sign example. That is an adversarial example issue. So the notion here is that you fool an ML system by providing malicious input, often involving very small perturbations to the pictures or whatever that cause the system to make a false prediction or categorization. So I can give you an example here. All of the pictures on the left, the school bus and the pheasant and the Mayan temple, are the original pictures. And then if we mask them with the column in the middle, that's just a mask where we're changing the values and the saturations of pixels, maybe the color of pixels a little bit. We put that over the original picture, we blend them together, and you end up with what humans would perceive as a school bus, a pheasant, and a Mayan temple. But what one particular machine learning system would see as a jaguar and a jaguar and a jaguar, absolutely for sure. Now, that's not how the human perceptual system works, but that's how machine learning perceptual systems can work. And it's important to understand that they fail differently than we fail. And there's a whole arms race in this adversarial examples where people are talking about systems to find them automatically and systems to protect against them. And it's just a big literature that's ongoing about that stuff. Now, the problem with adversarial examples is, though, there's a lot of coverage, and the attention is probably disproportionately large because the only risk that people talk about in machine learning is often this one. And it swamps out all the other important ML risks that we talk about. So it's important, it's number one, but it's not the only risk. And if we just address adversarial examples, we're not going to address the other 77 risks that Bimmel has been talking about in our work. Number two of the top 5, data poisoning. I already said that data play an outsized role in the security of ML system. Like I think I said at the beginning, I estimate that it's about 60% of the security risk is associated with data. So if an attacker can intentionally manipulate data being used by an ML system in a coordinated fashion, then the entire system can be compromised. Data poisoning attacks require really special attention because you have to understand what fraction of the training data an attacker could control and to what extent they could control those data. And in some sense, do brain surgery directly on your machine learning system. Really an important kind of attack that's not getting as much airplay as adversarial examples. The third in the top 5 is online system manipulation. I've already described to you that a system that's online can be continues to learn while it's out there in production. And so a clever attacker nudges the thing in the wrong direction on purpose, and this slowly retrains the ML system to do the wrong thing, or maybe quickly retrains it in the case of Tay. This risk is very complicated because if you think about it, the risk demands that ML engineers consider where the data came from and how good they were in data integrity, the choice of the algorithm that they're using, and also watch the system while it's running in order to properly address it. You can't just handle this at one place. You have to handle it at all 3 of those places, or you're still susceptible to that risk in an online system manipulation attack. Number 4 is transfer learning. I described that because of economics, in many cases in the real world, ML researchers take systems that are already constructed, and they pre-train it, and then they fine-tune it later to do a specific task. And a data transfer attack takes place when a base system is compromised or otherwise unsuitable, making the unanticipated behavior defined by the attacker possible. Something that I think most of us in security would call Trojan functionality, and something that in the machine learning literature they call backdooring. That's a transfer learning attack in number 4. Finally, and very importantly, data confidentiality is our 5th of the top 5. Remember, data protection is hard enough to do without throwing ML into the mix. We're not very good at protecting data in the normal case. So now we're going to shove some of that data into an ML and cause even more problems. So one unique challenge is in ML protecting sensitive or confidential data that through training are crammed into the model is like something nobody's regulating. Nobody's sure what to do about that yet. So if I put super classified information into my, targeting system, should that targeting system be classified itself? Like how does that work? These are very tricky things. So subtle but effective extraction attacks against ML systems data are an important category of risk. And you need to understand that if you use something like medical data and you cram it into your ML system, a clever attacker might be able to cram it back out. So that is a very quick overview of what we've been doing for the last a couple of years at BIML, the Berryville Institute of Machine Learning. I hope you found this interesting. I am a big fan of new technology. I'm not a naysayer or a stopper. I don't think we're going to stop machine learning, but I do think we need to be cognizant of these risks, and we need to think about them while we're building and fielding these systems so that we don't end up relying on technology that has risks that we don't understand. Here's where you can learn some more about this. You can go to our website and download the architectural risk analysis from the results section. That's berryvilleiml.com. You can send me email directly. That's my actual email address. And if you're interested in my work, and especially my work in software security, which really inspired this work in machine learning security, it's really the same thing. We're talking about building security in to machine learning systems, not protecting it later or trying to recover from a disaster, but instead architecting these things right from the very beginning. So I think we have about 10 minutes left, and I would be happy to take some questions now from you guys. There are two ways we can do this. I'm going to let Vaughn be kind of the arbiter of questions, and I'll also try to check out the chat, but I'm not going to really be able to do that if I'm talking. So without further ado, I'm going to stop sharing my screen now and go back into view and hope for some questions from you guys.
Yeah, Diana, if you would please go ahead and allow people to unmute themselves. Please either raise your hand and I'll call on you, or you can type your question into your chat and I'll relay it. Gary, I see one already in the chat, which is will folks be able to get access to these slides?
Yes, I will send these slides to Diana, and this talk was also recorded, so the video recording of the talk and the slide should be available to you in PDF form.
And those will be on the CACR website, where we have the speaker series and we have an archive of each speaker. And I'll think I see Susan Coleman and Matt Cole both posted some links in live with your talk, so you can see Coded Bias and also the Berryville site there in the chat.
Excellent, thanks.
Do we have other questions?
Don't be shy. There are no dumb questions. Really, somebody just break the ice.
Well, let me, I will jump in. So first of all, Gary, let me thank you on behalf of the audience for raising, I think, what is going to be one of the most important topics in cybersecurity for the next, I don't know how many decades.
We're going to be in work for a long time.
I mean, I think about the topics that I was wrestling with when I started 30 years ago, and now I think about the complexities of something like this, and boy, have we changed. You touched on this a little bit in your talk, but one of the big challenges from my perspective that cybersecurity faces is purely one of economic incentives.
Yep.
Right, the rush to get a product out there of any is always so big that it's hard to do security up front. Do you see that same thing playing out here with the AI models?
Of course. I mean, the thing that worries me most, Noah, is not the economic kind of misbalanced incentives, but rather the fact that the people that are inventing and controlling this technology, the organizations, tend to be big, giant private companies that are using it to give you better ads. And so if you think about attention as the coin of the new realm in the new economy, I encourage you all to read the book Surveillance Capitalism, which is a fantastic book by, I can't remember her first name, but Zuboff. Your attention for this little device, your telephone, it's maximizing for you to pay attention to it. It doesn't care if you're happy or sad or politically motivated or angry or suicidal, doesn't care, just wants your attention. As long as your eyeballs are paying attention, then it hits its kind of engagement threshold. So I think that for me, getting back to your question, the most important aspect of this work is keeping an eye on Google and Amazon and Microsoft and Facebook. Facebook is by far the worst, but they're also doing by far the most interesting machine learning work because of the people that they have on staff. And I frankly think they're evil and I don't trust them. And so we built BIML, and we talk about what we're talking about to make sure that those companies can't just do some CYA baloney kind of security stuff and pretend they handled the whole thing, when in fact we have some very big issues to grapple with. So our view at BIML is that we want to raise these issues. We want to make it clear that we have to think about these things and ask these questions of our technology suppliers. And in some sense, even the playing field economically, consumer versus Google.
Well, you have successfully opened the floodgates on questions in the chat here. So is anything being done on a national government policy level to disseminate the awesome information you just shared?
Well, a little bit so far. I just gave a talk for the FDA. I guess it was last week, because my friend Kevin Fu, who's an academic at University of Michigan, is now a technologist at the FDA. And so I was talking with people that have to regulate medical devices, and there's machine learning showing up in all these places. So there are places where people are thinking about this. I know the FTC is talking about misuses of bias machine learning technology and figuring out what to do about that now. And I also know that I've been talking with some people that are working with DARPA, worried about things like autonomous weapon systems and machine learning for stuff like closing the OODA loop down. And these are all issues. So yeah, there are people that are worried about it in the government. The government is not leading in machine learning, and you should never expect them to. But the government hasn't been leading in technology for a really long time, pretty much since we donked somebody into the moon in the 70s. Yeah. That's either good or bad depending on your point of view. But that doesn't mean that we shouldn't do this work. It means we are behooved to do this work because the government's not going to do it for us. We can't expect the feds to protect us from this stuff. We're going to have to protect ourselves. And number one way to do that is to educate ourselves about the technology.
Yeah, we're going to run out of time here, but let me at least get one more question in for you, Gary. Do you foresee this should be independent of cyber attack taxonomies, or should it be integrated, for example, within the MITRE attack framework?
Yeah, that's a really good question, Robert. My issue with thinking about this as only attack is that attacks are not the thing here. The thing here is risks that we're building into these systems, not attacks that come at these systems later. Now, should you think about attacks in cybersecurity? Absolutely, you should. I mean, remember, I'm the guy who wrote the book Exploiting Software, which was really one of the first book about, zero-day attacks back in the 90s. And I thought we were going to get in big trouble for that. So I believe we should talk about attacks, but I don't believe that the way to approach the machine learning system stuff is through attacks. It's rather through risks, which then have associated attacks in some cases. Now, there's a group at Microsoft that's actually using the MITRE attack framework and has built a machine learning version of that. I participated in that work, but I was really not very pleased with the results, because I think that thinking about attacks first is the wrong way to go about this. We need to think about security engineering first. And so that would be my own propensity when approached with that kind of question.
Well, Gary, I want to wrap this up on time here, but thank you for your virtual visit. This was a great talk, and I hope to have you back in person sometime real soon.
I can't wait to be in Bloomington. Yeah, although I heard it snowed last night, so we'll wait till that's over.
It did. For everyone else, thank you. This concludes the speaker series for 2020-21. Please look for an announcement of 21-22 coming out hopefully before the end of the semester. And we hope to see you all over pizza again next year. But thank you, Gary, and thank you, everybody, for a great year.
Thanks. Bye, everybody.